All right, this is experimental psychology. These are the notes for correlation. So when we were talking with lab number one, we were asking questions about, do people take longer to pull out of a parking spot when someone is waiting versus not waiting? We could ask the question, do men take longer than women? And we conducted an independent samples t-test to answer these questions because we were looking at differences between two groups, right? So up until this point, we've really only talked about differences. Today, we're going to talk about relationships between groups. If I know something about X, does it tell me something about Y? If I know something about how much you exercise, does that tell me something about what your blood pressure is like, right? The relationship between two variables. The statistic that we use is the Pearson moment correlation. We talk about this as an R. And really this talks about the degree of a linear relationship between two variables. Now, in correlation, we talk about predictors and criterions. Typically, you can think of the predictor as the independent variable and the criterion as the dependent variable. But these are arbitrary, as we'll see in a minute. With relationships, there really is no causal arrow specified. So what is the predictor and what is the criterion just depends on what your research question is and how you structure your hypothesis. So correlation can range from -1 to +1. -1 is a perfect negative relationship. So for example, the time it takes to drive somewhere and how fast you go. So speed versus time. Generally speaking, and if we don't talk about friction or traffic or anything like that, generally speaking, there's a negative relationship between the time it takes to get somewhere and how fast you drive, right? As you increase the amount of speed, you decrease the amount of time. And that's what makes it a negative relationship. Increasing in one variable is associated with decreasing in another variable. Now, when a relationship is perfectly linear, that means all of the data points sit right on top of a straight line. So for example, an example of a perfect positive relationship would be the number of hours you work and the dollars you get paid. So if you work at Starbucks and you get paid $10 an hour, if you work 1 hour, you get paid $10, 2 hours, $20, 3 hours, $30, and so on. Okay. What makes it a perfect relationship is that it sits right on top of that one line. And another way to think about this is that if I know how many hours you worked, I can predict with 100% certainty how many dollars you are going to get paid, right? Because the variability in dollars paid is 100% overlapping with the variability in hours worked. Those two things are perfectly related. Now, of course, not all things are perfectly related. And so a correlation tells you about the degree to which these values fall in this range of -1 to +1. The closer that values get to 1, the stronger that relationship. So a correlation of 0.89 or 0.79 or 0.69, those are all strong relationships. The closer a correlation gets to 0, the more it means that there's no relationship. So no relationship is when correlation is close to 0. And when we look at this, this means that the data points are kind of all over the place, right? So for example, the number of pets you own and your body mass index, your BMI, right? There's really no relationship between the number of pets and your BMI. In other words, if I know something about the number of pets you have, that doesn't tell me anything about your BMI and vice versa. Now, I apologize in advance. This is another one of those slides that will show up in stats if you are in my stats class or if you've already taken my stats class. But correlation is the degree to which their variability in X and Y are shared and the variability is separate. So if you think of height and weight, for example, if you imagine this circle here as representing all the variability that goes into your height, your adult height, right? There's a lot of things that go into your adult height. So you could think of things like genetics. You could think of things like your diet growing up, maybe how much exercise you had growing up. There's a lot of things that go into predicting your height, right? And that is the variability in why you are as tall as you are today. The same thing is true here with y, right? You can imagine this circle is representing all of the variability in your weight, right? The amount of food that you had yesterday is going to influence your current weight today. But also things like genetics, right? How much exercise you get currently, right? These are all things that are going to predict your weight today, right? Now, what correlation is really all about is the degree to which there is shared variability and the degree to which there is separate variability. Okay? So the degree to which two things, genetics, predict or lead to both variability in height and variability in weight, we call that shared variability. But there are things that predict height and weight that are completely separate, right? How much you had to eat today is going to predict your weight. It's going to influence your weight, but it's going to have no influence on your height. Whereas genetics is going to have an influence on both your height and your weight. Okay. So you can think of this correlation, this continuum then, as the degree to which these two circles of variability overlap, right? When the two circles of variability are highly overlapping, right, then there is a strong relationship, right? The relationship between age and height. Generally speaking, as you get older, you also get taller, right? Especially if we start from childhood and only go up to 45, because when you get really old, then you start to shrink again. But that's a whole separate thing. But generally speaking, as you get older, you get taller, right? And so there's a lot of overlap. If I know how old you are, I can predict with a fair degree of certainty what your height's going to be. It's not going to be a perfect prediction, but I can predict because these two things are related. On the other hand, when we look at the number of pets you have in BMI, these things barely overlap at all, right? So if I know something about the number of pets you have, that doesn't tell me anything about BMI. The things that go into predicting how many pets you have are not related at all to the things that go into predicting your BMI. So usually I throw this cartoon up here and no one gets it. But this is one of those, remember when I said a couple weeks ago, I believe that reliability is not equal to validity. This is another one of those classic research methodology tropes, and that is correlation does not equal causation. Just because two things are related does not mean that one thing causes the other or vice versa. Right? Causation can only be determined by methodology. Remember, we talked about the three criteria that need to be met to have a causal conclusion, to make a causal claim. One of those is covariance, which is a correlation. That's a criteria for causality, but it doesn't mean that you have causality. You need to do an experiment to show that. For example, there is a significant positive correlation between arm length and IQ in children. Children who have longer arms tend to be smarter, right? This is true. Does that mean that arm length causes IQ? No. Does that mean that IQ causes arm length? No. It means that there is another variable, a third variable called age. As you get older, your arms get longer and you get smarter. And age is causing both of these things to vary together. Right? So just because two things are related, it doesn't mean that one thing causes the other. They could both be caused by a third thing. For example, the significant positive relationship between ice cream sales and drowning. When ice cream sales go up, drownings also go up, and that's because of summertime, right? Summertime, people are more likely to eat ice cream. People are also more likely to drown. It's not that people are trying to eat ice cream while they're swimming and they're drowning, right? Ice cream sales don't cause drowning and drownings don't cause ice cream sales. It's just that a third variable is causing both of these things. And so this is why we say correlation does not equal causation, because you can never know why a relationship exists or if there is a causal arrow in that relationship if X causes Y, unless you do an experiment. Now, correlation is what we call an effect size. It's a measure of the strength of a relationship, the magnitude of a relationship. Cohen is an author that your book, I believe, talks about, gives guidelines for what is a medium, weak correlation, 0.10, moderate, a strong correlation of 0.5. When we want to talk about statistical validity, we need to think about the size of the effect, right? So when we're looking at, when we're evaluating research papers, we're reading our articles for the final project, right? We want to think about the size of the effect. So if taking aspirin once a day decreases the risk of a heart attack and the correlation is 0.03, it could ask, is this important? Like if we look at Cohen's guidelines, we would say, well, no, that's a really weak correlation. But given the subject matter, and we're talking about decreasing risk factor for heart attack, we might consider this 0.03 an important correlation. In contrast, if playing video games is associated with a risk of carpal tunnel syndrome, 0.03, in this case, we're not talking about life or death. We might not think that this correlation of 0.03 is as important. So even though they're both considered weak correlations, we have to consider the context as well. Now, there is a relationship between the sample size and statistical significance. Generally speaking, the larger the effect size, right? So as your correlation gets larger and larger and larger, the more likely it is that that's a statistically significant correlation. Also true, the larger your sample size. So the more people you have in your study, the more likely that is to be a statistically, significant correlation. So for example, is this correlation significant, 0.35 with an N of 25? It is not. What about this correlation, 0.25 with an N of 60? Now notice, this is 10 points lower than the correlation before that was not significant, but guess what? This is statistically significant. And the same thing here, correlation of 0.2. This is 1/100th of a point lower, and it is still significant. Okay, so generally speaking, if you have a gigantic sample size, even really teeny tiny correlations will be statistically significant. So this is just something you want to be aware of when you are sort of consuming this information out in the world. Just because a correlation is statistically significant doesn't mean it's practically significant. Think back to the heart attack, right? A small correlation might be practically significant if we're talking about heart attacks, but not practically significant if we're talking about carpal tunnel syndrome. So for example, and this is funny, like I talk about this example all the time, and I never have taken attendance until recently. And so this is actually a question that I could ask, which is there a relationship between attendance and exam scores? So let's say for the sake of example, there are 30 classes per quarter and the exam scores range from 0 to 100. And the researcher has a research hypothesis that there's a positive relationship between attendance and exam scores. And let's say we do that study and we find a significant positive correlation, right? There's a significant positive relationship between attendance and exam scores. As attendance goes up, exam scores go up, right? When we have a correlation, we state the results in plain English. We say there is a relationship between X and Y. And then we also specify what that relationship looks like. As X goes up, Y also goes up. Or as X goes down, Y also goes down. Okay? As X goes up, Y goes down, right? These are the different ways we can talk about this. I give you this slide right here for the APA style in case you have to report a correlation when it comes time to do the results for your final project. So just make a note that this is here, because if you walk out of my results meeting and I say you need to report a correlation, go back and look at the notes. These are the notes you should look for. R, degrees of freedom. Here's the correlation. P is less than 0.05 if it's significant. So that is it for the correlation notes for this week. We will check the schedule to find out when we will be meeting next face-to-face.